Hello everyone, my name is Simon McIntosh Smith and I'm a Professor of High Performance Computing at the University of Bristol. And today I'm going to talk to you about some work we've been doing with Isambard 2. So this is the new upgrade to Isambard, in particular about what we've been doing with the new Fujitsu A64FX. So you've probably heard about Isambard before. Isambard 2 is the new upgrade. It's a £4.1 million project funded by EPSRC, that's our Engineering and Physical Sciences Research Council in the UK. Like Isambard 1, Isambard 2 has been run by a consortium. It's the Great Western Four Alliance of Universities, which is Bristol, Bath, Exeter and Cardiff, all in the southwest of the UK, along with the Met Office, where the system's actually hosted. HPE/Cray are a partner, as are this time Fujitsu and ARM. And we deliver a tier 2 service. So in the UK, that means it's a national service available to any researcher in the UK and actually beyond. The system upgrade was funded late last year, late 2019, and it's building on Isambard 1's success of being the first production ARM-based supercomputer in the world. And it's been a huge success. The system is full, it's busy, it's been running lots of real science. And people are just using it like they do any other supercomputer. So that's why we're now doing Isambard 2. Now, Isambard 2 has two main components. There's the production system, which has been doubled in size. So that's now 2 cabinets, so over 21,000 cores, still based on Marvell ThunderX 2. This is our workhorse machine that's doing lots of great science. It's a Cray XE50 system, so it has the Aries interconnect. And the other great advantage of that system is it comes with all of Cray's software stack. So have the Cray libraries, Cray compilers, all the Cray software tools for doing performance analysis, which is really, really useful, as well as all of the open source tools. So we have all the GNU tools, we have an ARM compiler based on Clang and LVM, and so on. So that's already up and running. It's constantly full, doing real science, all running on an ARM-based system, which is great. But possibly the most exciting part of Isambard 2 is the addition of a rack of Fujitsu A64FX processors, and that's in an HPE Apollo 80 system. And this is a sneak preview of what that looks like. Got some really nice new artwork to go on the front of this additional system for Isambard 2. So we have 72 nodes. They're connected together with 100 gig InfiniBand. 72 nodes at 48 cores each, that's 3,456 cores. Of course, most of our codes are memory bandwidth bound, so what we really care about is how much memory bandwidth we've got. Each one of those nodes has about a terabyte a second of memory bandwidth. So this is GPU levels of performance, GPU levels of memory bandwidth, but from something that's just a CPU. It's easy to use as a CPU. Being a system from HP, it has the Cray software stack. So again, we have a Cray compiler for A64FX. That's brand new. We've only had the system for a week, so we're only just getting things up and running. But that's coming along nicely, as well, of course, again, having the ARM compiler for A64FX and the GNU compiler. We're hoping to also add the Fujitsu compiler, and in fact, we're just trying to install that at the moment. So the A64FX you've probably heard about, but just in case you haven't, it's a 48-core new CPU based on ARM. It's 1.8 to 2.2 gigahertz. It's got a terabyte a second of main memory bandwidth from high bandwidth memory, HBM. That's the really exciting part, as well as nearly 3 teraflops of double precision performance, and that's from dual 512-bit vector units per core. And it's only under 9 billion transistors for all of that, which is actually really small by today's standards. And this is one of the reasons why Fujitsu gets such great energy efficiency with this design. It's a lot of performance from actually a fairly small, very energy efficient chip. Now, one of the things Isambard is great for is doing really nice sort of rigorous comparisons between different systems and different benchmarks. So again, we've only had the system for a week. We are still getting lots of things working, but we're going to do our best to share some early results with you. And what I'm showing here is just some headline numbers for the systems we're comparing. So we have our A64FX system. Actually, most of the results we're going to show are from we had remote access to an A64FX system before Isambard systems arrived. That's still coming up, but we're starting to verify these results on our own system. We've also got the existing Isambard ThunderX2 Marvell chips. Those are dual socket 2.5 gigahertz, so lots of memory bandwidth because they had 8 memory controllers per socket. Then we've always run some top bin Skylake dual socket servers for comparison. So those are 28 core, maximum cores, maximum clock speed, 56 cores in total, Skylake boxes. So those are 2.1 gigahertz, 2.8 teraflops per node with 256 gigabyte second peak memory bandwidth. And then we've also added in some Cascade Lake servers. Now we don't have a very top bin for these, but these are the ones that probably most people will be using. So they're 20 core per socket, 2 of those 2.1 gigahertz, so that's about 2 teraflops per node. These have got faster memory than Skylake does, so we've actually got more memory bandwidth in these Cascade Lake nodes than in our Skylake nodes, even though there are fewer cores. And for many of the codes, you'll see that's what really makes the difference. And then, as with all our previous Isambard research, we've taken care to, when we're compiling our benchmarks, we try all the different compilers, we try all the common sets of optimization flags, and then we report results for the best. So just to summarize, we can go into all the details later on, but summarize, on the A64FX, it may be no surprise that Fujitsu's own compiler usually produces the best performance, so we try all of them, including the Cray compiler now. That may change over time, but that's what it is today. For ThunderX2 on Isambard, often it's the Cray compiler that's the fastest. Very occasionally it's GNU, something like OpenFOAM. So it's not always Cray, but it's often Cray. Maybe no surprise again on the Intel processors, it's usually the Intel compiler that produces the best results. Again, occasionally it might be GNU instead. Again, something like OpenFOAM. GNU is often the fastest. We also, for the different codes, if they provided different configurations, like maybe they could do flat MPI or flat OpenMP or a hybrid of MPI and OpenMP, we would try all those different options and pick the best. Often it was flat MPI actually, which was the fastest, but we reported whichever was best. So we're really trying to show the best we can achieve on each platform. We want this to be as fair as possible a comparison, so we'll try our hardest to get the best performance with the best compilers and the best optimization flags, and the best configuration on each platform, so we've got a fair comparison. So without further ado, here's some results. And what I've done is I'm showing results for the A64FX versus our ThunderX2, Skylake 56 cores, that's 2 times 28 cores, and then the Cascade Lake 40 cores, that's 2 times 20 cores, for 4 different codes. So first code is BUDE, that's Bristol's own molecular docking code. This is a real application. What's a bit unique about it is it's a compute-bound code. So you'd expect processors with high floating point performance, and it's single precision. Should do really well for BUDE. Then we've got TLEAF, which is a mini app benchmark that's widely used, that does conjugate gradient methods. So that's a heat diffusion code. Memory bandwidth bound. Then we've got Cloverleaf, which again is a well-known mini app. That's a hydrodynamics code. And then another real code, OpenFOAM, which is a big well-known engineering code for doing computational fluid dynamics. And then what I've done is, because most of these have times that are in hundreds of seconds, so to make it easy to understand, I took those times and I normalized them so that we get the best performing processor gets a score of 1, and then everyone else gets some fraction of that. So somebody gets a half, they're half as fast as the fastest result we had for that particular code. So now if we look along the results, you can see A64FX is doing really well. So it's the fastest for 3 of those 4 benchmarks, for TLEAF, for Cloverleaf, and for OpenFOAM. And those are all memory bandwidth bound codes. So maybe this is no big surprise that it's the fastest for all of those, given that the A64FX has a terabyte a second of memory bandwidth, compared to most of the others had sort of 250, 300 gigabyte a second of peak memory bandwidth. So it's got a good three or more times more memory bandwidth, and that's showing up in the benchmarks. That's really good. ThunderX2 was doing pretty well for something like OpenFOAM, where it was only 10% slower than the fastest that we had, which is the A64FX. So that's really good showing from ThunderX2. And actually for BUDE, which is our compute bound code, which is one where A64FX should do well. At the moment, it's actually Skylake that was winning. It was even beating our Cascade Lake system, and that's because it was a top bin Skylake box that had 56 cores, and that raw compute was winning out. On paper, A64FX should be winning that one too. So these are all very early results. We don't know what's behind that yet. We need to drill in and find out what's going on. I'd actually expect A64FX to do better on that one in the future too. Again, on paper, it should actually be right up there. It should probably actually be potentially even beating the Skylake system for that. There's the Skylake box and the Cascade Lake boxes are actually delivering fairly similar performance because they've actually got fairly similar memory bandwidth, and that's what we're largely measuring here. That's again no big surprise. So the compute's only making much of a difference for the Butte benchmark, which is compute bound. So these are really good results for A64FX, especially given how early things are. Probably the most challenging code to build and run there was OpenFOAM. That can take hours to compile and run, even with a parallel build. So the fact that one's working and actually giving really good results, and it's fastest on A64FX, is really impressive. And don't forget, this is one A64FX CPU versus 2 of everything else, because everything else are dual socket boxes, and A64FX is really just intended for single CPU per node. So these are really, really impressive results. On a brand new system with brand new software, which is still untested, unproven, with a lot of improvements to come. So I'd expect A64FX to get a lot better in the future. So that's all really good. And I'd like to acknowledge the team in Bristol who've done all of this and got all of these results, especially Andre Paneru, who did a lot of this, Tom Deacon, and they've had support from Harry Waugh and Thor Lowe as well. So thank you very much, all of you guys, for putting this together with almost no time and on a brand new, quite raw system. So that was great work on their part. And look for more of this to come in the future. Within a few weeks, hopefully we'll have more results and a bit more detail. So anyway, Isambard is a service. You can get time on the system. It's easy to apply for time. Basically, you email me if you want to have a chat first, and then it's really easy to apply for an account via a web page. We can give you a small amount of time for free. If you want a big amount of time, then you have to apply for that either through an EPSRC access to HPC call, or some of the CCP consortia in the UK will also have time which they can allocate to you. So that's just a really quick update. In a nutshell, A64FX already looks pretty promising. It's beating cutting edge dual socket nodes, even though it's only one socket in most of our tests, and that's even with immature software. Expect that to get better in the future. It's been really easy to use. In most cases, we're just running unmodified code. So this is flat MPI code or hybrid MPI OpenMP. We're not having to go in and make any extensive changes to source code. Whereas we're seeing performance similar to GPUs. I mean, that terabyte a second of memory bandwidth and several teraflops of floating point, all from one CPU. That's fantastic, similar to a GPU, but with a significantly lower barrier to entry in terms of ease of use, taking you up unmodified MPI and running that, which is great. So Isambard 2, again, it's making all of these major technologies available all in one place. It's also got some AMD Rome processors as well as some Cascade Lake. We've just added some new NVIDIA Volta GPUs. So within one system, you can do some really rigorous like-for-like comparisons, which is great. So hopefully that's given you an update about what's going on. A64FX looks great. If you want to give Isambard 2 a try, please get in touch. Thank you very much.